Thank you, Shirley. So, good morning, everyone. My name is Aranya, and I'm a data engineer at Onextel. To begin with, it's an honor to have been invited as a speaker to this year's summit. I've been fortunate enough to have attended some incredible sessions today, connected by some incredible speakers. As always, I've gotten to learn a lot from the community. With this current talk, my goal is to give back by sharing how we have designed and scaled Apache Doris as the central OLAP backbone for Onextel. My goal today is to walk you through our real world journey with Doris, what has worked for us, what has not worked for us, and how we have gotten to the point that Doris now powers analytics for Onextel, handling hundreds of millions of events every single day. So I'll just start this show. So, before diving into Doris, let me quickly introduce Onextel, what we primarily do over here, and what was the initial challenge that we face. So, most of us are aware of the practice of receiving one time passwords, marketing, and transactional communications via channels like SMS, WhatsApp, and even voice calls these days. So that is where OneXtel comes in. OneXtel is a business communications platform that empowers enterprises to communicate with their customers via the channels that we just discussed: SMS, rich communication service, WhatsApp, voice calls, and emails. So the CPaaS that you see on the slide stands for Communications Platform as a Service. So every day across channels, our systems process around 400 million messages a day. Now, for each of these messages, multiple life cycle events are generated. By life cycle events, I mean when a message is submitted to our platform, we get a submit event. When a message is delivered to the end user, for instance, when you get your OTP delivered to you, we get a delivered event. Likewise, in a similar manner, for SMS, around 5 life cycle events are generated per SMS, and for RCS and WhatsApp, a total of 9 events are generated per message that we process. This takes the total number of events that we process for these 400 million messages to a total of 2 billion events in a day. Now, our legacy system is powered by Postgres, which is an OLTP system. So to this day, it is live on some of our environments and it reliably handles large traffic volume for us. The only challenge that we face with Postgres is that it is difficult to scale as the data volume grows. Now, what I mean by this is that as the data volume grows, the table sizes grow along with the data volume, the index sizes grow parallelly, but the query speeds slow down. They get slower with time as the data grows. On top of this, there are a bunch of overheads. For example, the overhead of performing vacuums, the overhead of performing re-indexing to the tables, to the indexes, and also the overhead of maintaining write ahead logs on the DB. So due to these reasons and for the scale, we needed an analytics platform that could track deliveries of these messages, manage billing for the organization, and report client campaign performances. All of this in real time. So this requirement led us looking for an OLAP system. So once we understood the scale of the data that we needed to handle, it became clear that we needed a unified OLAP engine that could ingest data continuously and serve analytical queries with minimal latency. So our requirements were not limited just to fast analytics. We needed a system that could act as a data warehouse for factual data for compliance and audit needs. We needed our platform to serve as a pre-aggregated data store for serving our real-time dashboards. We also needed a platform to act as a metadata and traceability layer, such that the life cycle of each message could be tracked end to end. With this in mind, we evaluated three of the most popular distributed OLAP systems in the market, which are ClickHouse, Druid, and Pino. Let me switch to another slide. So we evaluated these three distributed OLAP systems, and each had their own strengths. But we also ran into certain limitations for telecom-scale use cases. To start with, ClickHouse delivered great query performance, but the ingestion we felt wasn't straightforward. For instance, handling upserts and merges at scale, we required custom pipelines and additional engineering effort. Apache Druid, on the other hand, had a powerful ingestion architecture, but it came with a relatively complex architecture. For those who are aware of the Druid architecture, it comes with components like overlord, middle manager, router, broker. So for us, this added additional operational overhead, and we felt it would make long-term scaling and maintenance more demanding for our team. Lastly, we have evaluated Apache Pino, which performed very well for real-time dashboarding, but it lacked flexibility for more complex queries that involved a lot of joins. So for those who are aware, Pino has a multi-stage query engine, which at our time of evaluation seemed promising initially, but we felt that it lacked the maturity that we required for our workloads. Doris, in contrast, offered the best of all these worlds. It provided a single stack that supports real-time ingestion, upserts, and high-speed analytics without a lot of moving parts in its architecture. Not only is Doris SQL native, it is also simple to horizontally scale, and its architecture is simple enough that tuning and operations remain manageable even as data volume grows, which was a critical requirement for us coming from a legacy Postgres system. So we also conducted early benchmarking, wherein Doris performed well compared to the other OLAP systems that we tested. But something that proved out to be a differentiating factor for us, like among the differentiating factors for us, was the community support that we received. So yeah, we received a great community support from the VeloDB team. A dedicated Slack channel has been created for us by the VeloDB team on the Slack community. Also, a special shout out that I would like to give to Darren, who has been incredibly helpful like throughout our journey. So all of the factors that we discussed together made Doris the clear choice to power our data platform. And moving on. So once we had chosen Apache Doris as a OLAP engine, the next challenge was to design an architecture around it that would allow us to meet Onextel's Telecom-Scale goals. So the diagram that you see on your screen shows how Doris sits right at the center of the Onextel data platform. To walk you through our architecture, as you can see on the left hand side of your screen, all message events originate in Kafka, which receives, again, as we discussed, 5 lifecycle events per SMS and 9 lifecycle events each for RCS and WhatsApp. Uh, so Kafka again is coordinated by Zookeeper and serves as a real-time event backbone. On top of this, we have on top of Doris, actually, we have multiple integration layers. For example, our Spring Boot based API uses JDBC to serve dashboards and client-facing portals. For example, delivery analytics, campaign summaries, and even billing data. We also have Python-based asynchronous jobs that is triggered by the Spring-based API layer. So we have these asynchronous jobs for heavy workloads that require a large chunk of data to be returned. These are usually user download requests. So these interact with Doris via the arrow flight protocol, which you can see on the top arrow of your screen. So what arrow flight protocol does is that it provides an interesting optimization, which is given out of the box by Doris. We'll be discussing this in subsequent slides. Yeah, we covered our API layer, which again triggers certain asynchronous jobs which use the arrow flight protocol, which is an optimization that Doris provides, which we'll be discussing in the coming slides. On the observability layer, we have Prometheus and Grafana. So Doris exposes certain native metrics that we scrape using Prometheus and visualize through Grafana. This setup lets us track our cluster health, the ingestion lag, and the query concurrencies in real time. Finally, on the right hand side, we have the AI and analytics layer, where tools like Apache Superset and Doris MCP framework connect directly to Doris to provide visual, basically BI and AI to serve our BI and AI use cases. They provide visual analytics and on-demand natural language query capability to the end users. So with this foundation in place, the next focus area for us was to how we can model our data efficiently to balance correct data correctness, performance, and scale. So that is what we'll look at next. So one of the biggest strengths of Apache Doris is the flexibility of its table models, and we actually use all three of the table models that Doris provides in our production setup, and each serves a very distinct purpose for us. Starting with the unique key model. So the unique key model ensures that uh, with that a table is uniquely identified by a key, and Doris automatically keeps the latest version of that record, making it perfect for absurd scenarios. So in our case, as we have discussed, that each message that we handle generates multiple life cycle events. So using a unique key model, we observed all events for a single message for a particular channel into a single consolidated row. The diagram that you see on your right is a sample representation of how absurd works for us. So on the top end of the diagram, you can see individual events from different Kafka topics that are switched stitched together to form a unified row per message, which you can see on the lower part of the diagram, which is always up to date and clean. So this also results in an 80 to 90% reduction in the amount of data that Doris needs to scan as compared to raw event storage. Next, we have the aggregate key model. So in OLTP and most data warehouse architectures, aggregations are usually built after ingestion. So mostly using scheduled batch jobs or materialized views that periodically roll up the fact data into summary tables. But Doris gives us something that is far more efficient as compared to this. So with the aggregate key model, aggregations are handled during ingestion time itself, and there is no need to recalculate these on every query that we fire to the database. So on ingestion itself, all the aggregates are calculated. So Doris stores these pre-computed values, things like totals, averages, counts, and rollups that our API can query. API queries these basically in constant time, requiring no complex queries and no heavy joins. Uh, this has also had a massive performance benefit for us, with our summary dashboards consistently responding within 200 milliseconds. And again, this has resulted in a reduction of number of rows scanned by orders of magnitude. So this ensures that even if our fact tables continue to grow into tens of billions of rows, our reporting performance remains predictably fast, and it also remains operationally stable. Lastly, the final data model that Doris offers is the duplicate key model, which keeps every single record intact. So this is what we are using for metadata logging. For instance, we log all our API requests in an API metadata table. We log all the Kafka events that we get in a Kafka metadata table, and so on. So the benefit of this is that we don't lose any traceability here. So in this scenario, Doris key tables are ideal, and I would say they're pretty solid. For instance, in the example that is there on the screen, we ingest individual events from different topics as they are into the metadata table. This helps us identify system discrepancies. For example, the right hand side of the image that you see, the image shows two delivery events being received for the same message. So that could be highlighting a potential system discrepancy. Therefore, with this model, we are able to maintain audit trails and perform quicker and, I would say, smoother troubleshooting of our system. So together, these three models that we have covered as part of our slides address all three of our business and technical requirements that we discussed in a previous slide, and let us balance data correctness, size, and query speed. And I believe that these models, although again, these models have been a key reason why we have been able to achieve the scale that we operate at. Moving on, for a telecom platform like Onextel, analytics is not just about insight. So it directly affects customer experience. So imagine getting an OTP 30 seconds late. Not only is it a failed login for you, it is also a lost transaction and a bad consumer experience. So, for an organization like us, latency is extremely critical, and it is a part of the SLA, the service level agreements as well. So, when we designed our data pipelines, we wanted something that could read directly from Kafka with minimal ETL and without much of custom ingestion code, just to keep up with the scale. And that is where Doris routine load became a perfect fit for us. So routine loads give out of the box streaming ingestion fully managed within Doris. Now the way these routine loads are configured by default are pretty solid, I would say, but there were certain parameters that we had to play around with in order to match our telecom-scale requirements. So the parameters that you see on your screen are some of the parameters that we had to tweak, we had to benchmark and tweak based on our use case. And we can we can just skim through these parameters for once. So starting with desired concurrent number, it is basically the number of concurrent tasks you can have per routine load job. So each task is responsible for consuming a portion of the data and then loading it to Doris. Now, mind you that each individual task independently consumes resources of your backend node. So, careful tweaking of this parameter is would be advised, not to overburden your backend nodes. But in simple terms, more tasks mean more parallel processing. Then we have the max batch interval and max batch size configurations. So for those who are aware of Kafka configurations, these are quite similar to log flush interval parameters in Kafka. So these control the batching of the data before it is processed by a single task. So max batch interval is nothing but the time a task would wait before uh, starting processing that batch. Whereas the max batch size is the amount of data a task would wait to accumulate before that batch is tried to tried to be processed. So a task is basically triggered when either match batch interval seconds have passed or uh, accumulated data size reaches the max batch size. Now, lastly, we have the group commit configurations. Mm, Now, real-time ingestion is nothing but very high frequency of batch ingestion operations, right? Where each batch operation triggers a new data version to be created. Uh, the data has to be written on the disk, and the metadata corresponding to that data needs to be updated. So all of these operations in each of the right operations that are performed in background, consumer put a lot of IO pressure on the system. So in order to relieve the system of this IO pressure, we can utilize group commit configurations. what they do is that they batch multiple small write operations into larger write operations, combining multiple small writes into single larger write operations, eventually reducing the IO pressure on your system. So these were certain routine load related parameters that we tweaked for our use case. Another data loading mechanism we use for our API and Kafka metadata logging is the stream load module. It uses the HTTP protocol to ingest batches of data into Doris. Stream load is again highly performant and secure and suits well for our metadata workloads. So the key idea over here is that Doris is highly tunable and it provides reliable and fast ways to load your data into the platform. So you can simply shape the system to your workload instead of shaping your workload to the system. Moving on, so we've all seen systems where dashboards break during peak load or insights that lag behind reality. That is, they show stale or outdated data. So such a scenario simply cannot happen in a telecom environment. So we have built our analytics layer to be fast, fault tolerant, and always on. So we have developed a Spring Boot based API layer to serve the data that Doris stores to power again dashboards and client campaign portals. So our API layer uses Hikari for connection pooling and Hibernate for ORM. As discussed during our architecture slide, that the API layer also triggers certain Python-based backend jobs that are triggered asynchronously for requests that require heavy chunks of data to be returned. So since Doris stores data in a columnar format, when regular JDBC or client connections try to pull data from Doris, it has to be firstly serialized to a row-based format in transit, and then deserialize back at the client end. So this process of serialization and deserialization adds significant overhead that the Aeroflight protocol eliminates by sending columnar data straight to the client. And this results in query performance up to 100 times better than your regular JDBC connections. And trust me that this is no exaggeration. Query performances of up to 100 times can be observed with the Aeroflight protocol. Now that we're discussing about query performance, let's try to dig a bit deeper into that. So when we think about query performance, we usually tend to think in OLTP terms. So in case of OLTPs, index lookups are the primary drivers of performance. But with Doris, like any other OLAP, data skipping is where the actual performance boost comes from. So data skipping in Doris is enforced via factors such as partitioning and bucketing of data. So as Parth said in the previous session that partitioning and bucketing of data is extremely critical. I'd like to continue on that, and those are actually quite critical configurations that you have to set. So these are usually done based on your common query parameters. For example, you may partition your table by date, and for all queries that require today's data, will not have to scan months and months of older partitions. So that results in lesser amount of data scanned and faster queries. Likewise, sort key and the sequence of columns that you set for your table also drive performance due to something called the prefix index that Doris creates internally. On top of these, you can always add indexes and filters based on your query patterns to boost your query performance further. Now if ingestion or query starts slowing down, we must know before a client sees the impact, or if there is a major impact internally. So we must know before that happens. So as we discussed, Doris again exposes native metrics that we scrape using Prometheus and visualize using Grafana. So with our Grafana dashboards, we are able to track cluster health, performance, ingestion lag, query concurrency, all in real time. We also have alerts set up for all these metrics. So the moment something deviates from the baseline, alerts are fired, and those alerts allow us to resolve those issues proactively instead of resolving those reactively, which can lead to firefighting scenarios and creating difficulty for everyone. So those scenarios are avoided based on the alerts that we receive for whenever something deviates from the baseline. So yeah, we were discussing about cross-cluster replication. So it is another feature that Doris provides out of the box that ensures that even if a particular data center or a region becomes unavailable, the platform continues to operate without interruption using a standby cluster. So cross-cluster replication involves a syncer process that constantly replicates the changes that are done to your primary database to your secondary database. And in an event of a failover, in an event of a disaster, a quick failover is done from the primary to secondary, resulting in high availability during such disaster scenarios. So this again helps us maintain a fault tolerant system that is always available. So all of the things that we discussed as part of this slide uh, help us build a platform that is always on, that is always accurate, and that is always fast, even at the scale that we are operating at. Moving on, we'll cover some initiatives that are currently a work in progress for us. So more towards BI and AI use cases. So firstly, we use Apache Superset on top of Doris for visual analytics. Uh, Superset lets us build interactive dashboards directly against Doris with minimal latency, even on billions of rows that the database stores. Using Superset, our internal teams can visualize insights like traffic patterns, delivery performance, even latency distribution, all in real time without requiring any engineering intervention. So some examples of the visualizations that we have built so far. The one on the left, you can see comparison between different delivery statuses. So the black line showcases the number of messages that were submitted on the platform, whereas the blue marker indicates the number of messages out that were delivered to the end user. The representation on the right shows region-wise distribution of traffic on our platform. So this is the map of India, and it shows us the regional state-wise traffic volume for the country. So moving on to something more interesting and something we are actively building towards is AI-assisted analytics over Doris. So we have integrated Doris with the Model Context Protocol, which too is an open source option made available by the Doris community that allows LLMs to connect with live data on Doris. So just like USB is your standard way of connecting an external device with your laptop, you can consider MCP as a standard way of connecting large language models to a live data source. So we are utilizing MCP. We've connected it with we're connecting large language models with Doris via MCP. So this means users can ask questions in plain English or a language of their preferred choice, such as what was the latency distribution for SMSs for yesterday, and the system would automatically generate an optimized query for Doris that the same query would be fired on the platform. The results would be returned, and sometimes even charts and summaries out of the returned data would be presented to the user. So the vision over here is that you should not need SQL expertise in order to access data insights from all the data that you have stored on your system. certain examples, again, certain in development examples right from cursor that we are using for MCP are on your screen. On top of the screen, you can see the natural language queries that the user has fired and the corresponding outputs for the same. The one on the left shows the user asking for the latency distribution for SMS channel or for a particular date. The output is again visible to you. The one on the right, again, a natural language query, which is asking for hour-wise delivery status, again for SMS channel for a particular tenant with for a particular customer on a mentioned date, and so is the data returned by the protocol. Corresponding data is again visible to you. So while this AI layer is still in development for us, the early results are extremely promising, and we see it unlocking self-serve analytics for our internal teams in the future. And all of this, again, as we know, is backed up by Doris in real time. So as we move towards the end of the session, I would want to quickly show you as to where we are headed next, as we feel that our work with Doris is still well in progress. So, based on the diagram, the first major focus area for us is a move towards a unified lakehouse architecture with with Apache Iceberg acting as a data cataloging and governance layer. So with this, we'll be able to achieve capabilities like time traveling, schema evolution, and ACID guarantees on our data lake, which in turn would help us manage all the data that we are managing currently more efficiently. And we plan to introduce a Spark cluster to power our ETL jobs. And we also plan to integrate Spark's machine learning libraries for our planned ML use cases. And again, Doris will continue to remain the core serving layer of the platform. The second part on the roadmap is scale. So our current architecture comfortably handles around 350 to 400 million messages every day, but we are moving towards and designing for a billion plus messages per day, which would translate to around 5 billion events when life cycle events are factored in. So 5 billion events in a day, the capability to handle that is what we are headed towards. The roadmap also includes extending analytics to other communication channels, such as the voice platform. So all the data that corresponds to the voice, the automated voice calls that you may have received. So all the data related to that, we need to expand our platform so that we can handle that kind of data as well. And subsequently, other channels of communications as well, such as emails and chatbots, which would give us a true omni-channel view across all communication platforms. Finally, on the AI front, what we showed you earlier is quite honestly just a starting point for us. We have just started to scratch the surface for the AI use cases. So we plan to further expand on the natural language analytics. We want to even build ML based anomaly detection and also explore intelligent routing models so that that can learn from the historical campaigns that we have been conducting for all this time. So I think that basically sums up the part that I wanted to cover as part of the session. Again, our journey with Doris has been extremely rewarding, but we feel that the most exciting part still lies ahead of us. So we're looking forward to learn, continue learning and contributing to the Doris community. Yeah, over to you again, Shirley.